Okay, so hi, thank you for allowing me this opportunity to present our study here. And today what I'm showing here is like a few clips of a computer game. It's called Whack-A-Mole. And in this computer game, the player pays attention to the hole over a certain period of time up to the appearance of the mole. When the mole appears, they have to react as soon as possible to hit it in the head with a hammer. And what I'm interested in is what happens here during this waiting period. And that's what I'm calling here attentive anticipation. And this attentive anticipation, as is already been kind of slightly suggested by Sarah, is characterized by this cardiac deceleration. So the heart starts beating slower during the attentive anticipation, and this kind of correlates with faster reactions in these kind of tasks. And the question I was trying to address here in this study was, so this state of attentive anticipation is characterized by a certain pattern of neural activity, and this neural activity will cause the heart rate to slow down, will also cause facilitation of sensory motor processing, but does this slowdown of the heart actually interferes or has a direct impact in the sensory motor processing? And as Sarah already hinted to, is like this slowdown of the heart rate causes enhances diastole, so it means that there's a bigger period of kind of quietness in the heart that can facilitate sensory processing. But I was interested in understanding if the neural responses to heart rate actually also change with heart rate. And so there's also other studies that show not only during attentive anticipation we see this cardiac deceleration that will interfere with sensory motor processing, but also just ongoing fluctuations of heart rate can also interfere with sensory motor processing, meaning that as the heart rate fluctuates from one moment to the other, periods of slower heart rate are associated with more efficient sensory motor processing. And so how can the heart then interfere with neural processing? And one mechanism is, so the heart, each heartbeat will evoke a neural response in the brain. The heartbeat evokes potential that can be measured, for example, with EEG. And this heartbeat evoked potential has been shown to correlate with the efficiency of sensory processing. So if we're measuring the amplitude of this heartbeat evoked potential immediately before the presentation of a sensory stimulus, the amplitude of the heartbeat evoked potential will predict if the participant is able to detect the stimulus or not. And so there's this idea, and this usually is observed in a way that the higher, a more positive amplitude of the heartbeat evoked potential is associated with worse sensory processing. So maybe these neural responses to the heartbeat might be interfering with neural processing in the brain. And so the hypothesis that I wanted to explore in this study is that the slowdown of the heart rate might change the amplitude of the AGP, and by changing the amplitude of the AGP might facilitate sensory motor processing. And in particular, in this study, I'll be exploring these connections. So does changes in heart rate change the amplitude of the AGP? And for this, I used a data set that had been previously acquired in the lab. And in this data set, we have a young group of participants with mean age around 23, an older group of participants with mean age around 60, and we acquired EEG, ECG, and pupillometry. And we acquired this data while the participants were engaged in these two different task conditions, so a simple reaction time and a go-no-go task condition. And these task conditions, the trials have the same kind of structure, so they start with a warning stimulus, and then around 2 seconds later, a target stimulus is presented. In the simple reaction time task, the target stimulus is always a go stimulus, and participants just have to press the button as soon as possible. And then in the go-no-go task, the target stimulus can be a go stimulus or a no-go stimulus, and the participants are instructed to press the button to the go stimulus and refrain from pressing the no-go stimulus. And between the warning stimulus and the target, that's what I call the attentive anticipation, and that's the period I'm interested in. And so when we measured heart rate in this task, and we looked at the heart rate between the warning stimulus and the target, so what we see is that there is a decrease in heart rate. So the warning stimulus induces this heart rate deceleration, and then the target appears, the participant presses the button, and then we see this acceleration in heart rate. And then what we see is that older adults, so this is for young adults, for the older adults, this cardiac deceleration is significantly decreased. So we're interested in seeing if during this period of cardiac deceleration, do we see a change in the amplitude of the AGP that might explain differences in sensory motor efficiency. And we're also interested in seeing if this is different between young and older adults, given that the older adults don't show such a strong cardiac deceleration. So first, before we go into that, I wanted to show you that we can actually measure the heartbeat evoked potentials in this data set. And we measure the heartbeat evoked potentials by aligning the EEG recording to locked to the T wave. And we measure, so the heartbeat evoked potentials can be measured locked to the R wave or to the T wave. And we opted to lock them to the T wave because then after the T wave, we have this calm period of the ECG, so we're measuring the heartbeat evoked potential in the absence of this electric cardiac artifact. And so what we did also is like we locked to the T wave, but we baselined to a period just before the QRS complex. And so this is what the potential that we observed. So this is a central parietal midline EEG channel, so located here on the top of the head. And what we can see, so the 0 is the T wave. After the T peak, we see this positive potential. That's the neural response to heartbeats. And what we can immediately see is that this response is significantly stronger in older adults than in young adults. And here we can see the topography of the response. So we can see here on the top of the head, we have these, the stronger amplitude of this potential, and is significantly stronger in older than young adults. And this has already been seen in previous studies, and it's still not clear what's the functional significance of why older people have stronger AGPs and how these might impact their performance. And we also studied here the AGP separated by task condition. And so for the simple RT, we have in blue and the go-no-go in orange. And we see this positive potential after the T peak. And we don't see any significant differences across tasks. And so we measured this AGP by just using the whole recording. So we have like 16 minutes recording of the participants on each task, and we just measured the AGP averaged across the whole time of the recording. Now, what we wanted to do is to study if the AGP locked to this period of the task actually show the difference. So if the warning stimulus induced the state of attentive anticipation, that was characterized by a different amplitude of the AGP. And so we measured the AGP here and compared with the AGP just before the warning stimulus. And what we observed was there was no significant differences. So the AGP before the warning stimulus is here, in blue, and after the warning stimulus in black. And you can see for the older group or for the young group, we didn't observe any significant differences. So, but we're interested in this idea that cardiac deceleration might change the AGP, but in this particular task, there was quite an easy task, and there was a relatively short period of attentive anticipation. The change in heart rate that we observed induced by the warning stimulus was relatively small, only around 1 beat per minute. And if we look at the fluctuations of heart rate throughout the whole task, we can see that these fluctuations are a lot larger, so around 30 beats per minute. So we decided to also explore these kind of ongoing fluctuations of the heart rate that are not locked to any task event, and try to explore if these were associated with the amplitude of the AGP. And when we do this, and here I'm showing the AGP divided for slower heart rates, so when it's calculated in cardiac cycles that are slow cardiac cycles, we can see that the AGP shows an amplitude that's more positive for the slower heart rates and less so for the faster heart rates. So immediately we can see that this hypothesis that maybe the slower heart rate will be associated with a smaller AGP that might interfere less with sensory processing, that doesn't seem to be the case. In here, we can see that the slower heart rates are associated with a larger AGP. Also, we can see that this effect of heart rate appears to be stronger when we measure these during the go-no-go task than the simple RT task. And so this is just another way of seeing the same data. So here we have all the EEG channels on the y-axis and time on the x-axis. And here I'm just showing all the data points where we saw significant regression coefficients between the amplitude of the AGP and heart rate. And we can see a significant effect in occipital parietal channels for the simple RT and the go-no-go. But for the go-no-go, these regression coefficients were stronger, and we can see the significant relationship expanding up to the frontal channels. And so here, we can also see, if we compare the regression coefficients across the different tasks, we can see a significant effect of task here at the end of the cardiac cycle. So this was quite puzzling because, okay, we show now that the AGP shows a correlation with heart rate, but it shows a correlation with heart rate that depends on the type of task that participants are engaged in. And so we looked at different task parameters that might explain this difference, and we looked at average heart rate of the participants while they were performing one task or the other, and we didn't see any difference across tasks for average heart rate variability, or the range of heart rate during the task. We see differences across age groups in the direction that's supposed. So older people have slower heart rates and less variable heart rates, but nothing. This aspect doesn't seem to be able to explain the differences. And also, we looked at the differences in arousal level and differences in cortical excitability by looking at pupil size during the simple RT and go-no-go. That's an indirect measure of arousal, and the power of alpha oscillations, that's a measure of cortical excitability, and none of these measures showed any significant difference across tasks. So we were quite puzzled by this idea that maybe the AGP depends on heart rate, but it depends on heart rate. This relationship depends on the type of task the participants were engaged on. And so we took advantage of also having a passive task condition in this data set, and this task condition was acquired always at the beginning of the session, and we only had 4 minutes of recording. And in here, the participants were listening to the warning stimulus. And they didn't have to do anything. So they listened to the warning stimulus with the same frequency that was played in the other tasks, but they were just fixating a gray screen and they didn't have to respond. And when we looked at the effect of heart rate on the AGP under this condition, we didn't find anything. So there was, under these conditions, that participant was not engaged in a task, the AGP did not depend on heart rate. And here is just showing that if we use only 4 minutes of the simple RT and go-no-go task, we can still observe a significant relationship of AGP with heart rate, and this is shown here in blue and orange. You can see that the regression coefficients are still significantly different from 0, but for the passive condition, the regression coefficients are always significantly, are not significantly different from 0. And so, in conclusion, what we found no evidence that the AGP changes during attentive anticipation in these warned reaction time tasks, but the AGP does show an effect of heart rate, and that this effect of heart rate depends on the cognitive state of the participants. And so what might this mean? So one way is that the AGP, the brain receives input from the heart, and that input is transformed into this neural response to heartbeats on the AGP, and this input might depend on heart rate. And the way this input is transformed into the output, the AGP amplitude, will depend on neuronal gain. And so if we're in a cognitive state that's characterized by high neuronal gain, then we have an output with a large range of amplitudes. If we're on a cognitive state characterized by low neuronal gain, then we have a smaller range of outputs. And maybe this relationship between the AGP and heart rate can be used as a marker of neuronal gain that's associated with the cognitive state of the participants. It also means that the spontaneous heart rate fluctuations might interfere with sensory motor processing through the activation of these neural responses to heart rates, but these might depend on task difficulty and cognitive state. So we will only find an effect of heart rate where for slower heart rates, for example, might be beneficial for task performance if we're in a cognitive state that's associated with a more difficult task condition. And this has been seen in some studies that show that the effect of heart rate is only detectable if we're using tasks with the stimulus being presented at the threshold of detection. Okay, that's it. I would like to thank all my collaborators and funding agencies and you for listening. Thank you.